This webinar is produced by the U.S. EPA's Office of Pesticide Programs. The views expressed by our presenter are for educational purposes only and do not represent the official views or positions of the EPA. Welcome again. My name is Kuei Wen. I'm a Chemical Review Manager in the Office of Pesticide Programs. I am your moderator today. In today's webinar, we will review the similarities and differences between ground and aerial pesticide application. We will discuss some of the technologies available for ground application, and we will wrap up with an intensive discussion of the biology of weed management. This webinar is part of a larger EPA effort to promote pesticide spray drift management and promote the conservation of native habitat. This is the last of a three-part series intended to educate stakeholders on ways to reduce pesticide spray drift. The first webinar occurred on March 15, 2018, and was presented by Dr. Greg Kruger. It covered the fundamentals of pesticide spray drift management. If you missed the webinar, the materials are posted online at the link shown on the screen. The second webinar occurred on September 27, 2018, and took a closer look at aerial application. It was presented by Dr. Bradley Fritz of USDA. Today's webinar will take a closer look at ground application and will be presented by Dr. Greg Kruger. Dr. Bradley Fritz will join us again today for the Q&A discussion. Just to give you an idea of who's in the room with us here, Dr. Fritz presented the September aerial application webinar, but he is also joining us again today for the Q&A discussion. He is an agricultural engineer at the United States Department of Agriculture. He is currently the research leader of the Aerial Application Technology Research Unit at the USDA's Agricultural Research Service in College Station, Texas. His research spans the broad area of agricultural application technology with a focus on aerial pesticide application. You can check out his latest research at the link shown on the screen. At this time, I would like to present our speaker. Dr. Greg Kruger is a weed science and pesticide application technology specialist from the University of Nebraska-Lincoln. He is the director of the Pesticide Application Technology Lab at the university. His research covers areas such as droplet size and efficacy, spray drift deposition and canopy penetration, and the influence of nozzle type and other parameters on droplet size. He is also the Weed Science Society of America's liaison to EPA, and provides technical expertise to EPA on matters related to weed management. Please welcome Dr. Kruger.
All right, good afternoon or good morning to you if you're on the West Coast or other places around the world. It's a real privilege to get to do another one of these, and thank you, Kuei, for helping put these together. They've been excellent so far, and I'll try to hold up my end of the deal over the next hour. For many of you, you've been online for these already, and you're probably familiar. But I thought before I got too deep into it that we would do just a quick review. Like I do with every single one of my talks, I always like to give credit where credit's due. And today I get the opportunity to present research from a lot of the different students and technicians that have been in my group over the past 9 years. So I know several of you are online and listening today, and you guys are part of the reason that we've had the opportunity to share this type of information. So just a quick review of the first two webinars so that we can kind of lay the foundation for anybody that might have missed one or both of those. Spray drift, I think it's important to have a definition so that we're all talking about the same thing. This definition of spray drift that I'm going to be using throughout this presentation, and the same one that we've used for the last two, is the movement of spray particles and vapors off target, causing less effective control and possible injury to susceptible wildlife, vegetation, and people. It's not a definition I came up with. It's from the National Coalition on Drift Management from 1997. And again, like we talked about the first time, there's really two different things that you should note in there, and that's that there's two different types of drift. First one being vapor drift, and this is associated with volatilization or the conversion of that pesticide application to a gas and moving off target in that state, and particle drift, which is the movement of spray particles during or after the spray application. So when we talk about the drift, drift really encompasses both. Like the first webinar I presented and much of what Brad presented in the last one, then we're going to have a heavy focus on the particle side. We're really not going to get into vapor drift today. Now, just a quick review on particle drift. Again, if I've got any aerial guys in here that were on the webinar for Brad, keep in mind that as Brad pointed out in that webinar, things can be a little bit different from the aerial application side than the ground side on some of these factors that we talk about, yet some of these principles are going to hold true across both application platforms. But most of what I talk about today is going to be heavily focused towards ground applications, again, kind of circling back to where we started. So the big 4 factors we talked about were wind speed, and coupled with that is wind direction. The second one that we talked about in terms of being very important for mitigating drift is understanding boom height and minimizing boom height as much as possible. The closer we get to that application target, the more effective we are going to be at depositing those smaller droplets. The third one we talked about in that first webinar was the distance to susceptible vegetation, and we really can summarize that up into one simple word, and that's buffers. So the greater the buffer distance, the less likely we are to see off-target movement into those unintended areas. And the last one, which we had spent the most time on, is spray particle size. And this is the one that really we start to see some differences between ground and aerial applications, with differences in use of pressure, nozzle selection, orifice size, and flow rates. So particle size becomes a very key player in terms of off-target movement. Obviously, the larger the droplet size in both cases, the greater the deposition rate or the less drift we're going to see. So just as a kind of a recap and a reminder, we've got these 2 videos here showing 2 different nozzles. Both have very, very different droplet sizes and very different drift potentials. The one on the left is an XR nozzle, and you can kind of see that black or gray hazy background. That's all those fines that are hanging in the air, and those are the ones that are going to have the highest potential for drift. On the right-hand side is the extreme opposite for our ground applications, and that's a TTI 11004. Again, you can see how we've managed to get rid of that black hazy background with all those fines, and we've got an ultra coarse spray quality here. And when we talk about managing particle size, nozzle becomes the first point that we would start in terms of talking about droplet size. So then, based on the past research, we know that about 72 to 75% of that change in droplet size for ground applications is going to be attributable to nozzle selection. Now, this is where we're going to kind of change focuses a little bit on today's webinar versus the first 2 webinars, and we're really going to get into delving in deep in terms of the relationship between drift and efficacy, talk about the efficacy component and what we can do to optimize applications from an efficacy standpoint, and what we might be able to do in certain cases to minimize drift while optimizing the efficacy of that particular product. And the reason we want to talk about this is that if we're not effectively managing the pest, we're really not out there using that pesticide for the purpose it was intended. So our first focus has to be on managing that pest that we're out there trying to control. And then within that framework of that, we want to try to mitigate drift as much as possible. Keeping in mind, I think it's really important to note that we are going to see some off-target movement with every application. I think it's easy to forget that when we don't see it, but we are going to have some off-target movement with every application. Now, this is another slide that we used in the first round, and this really shows the complexity of that pesticide application. And we talked about the drift component on that right-hand side and what's coming off from the atomization, the volatilization, from the atomization and deposition processes. Today, we're really going to get down and try to get to that biological effect, focus on that. and then talk about how we manage those processes from there. So I just want to start with talking about a couple different efficacy trials that we've done over time, and how those kind of different trials show how droplet size is important from an efficacy standpoint, and then we'll try to tie that back into the drift reduction and off-target movement piece in a little bit. So this is some work that was done out in western Nebraska. This is looking at triazine-resistant kochia. What you see on this slide is the control ratings at 9 days after application, using 3 different nozzles, an XR, a DG, and a TF or turbo flood. And those nozzles were operated at 30 psi. The application was using paraquat and atrazine, so we really got only one effective mode of action on that triazine-resistant kochia, and that's the paraquat. We know that paraquat is a contact-based herbicide, and so really what you're going to see in this is driven off of that activity of the paraquat in that application. And what you see, we've got 3 sets of bars there going across the x-axis. We've got 10 gallon per acre, 7.5, and 5. And we've got 3 different nozzles at each of those applications, giving us 3 different droplet sizes, a medium, coarse, and extremely coarse. And so if we just kind of focus in on that 10 gallon per acre, those brown bars to start with, what we've got on the y-axis is control, and we've got our control ratings on a scale of 0 to 100. So I see that there's many of my colleagues online very familiar with this. If you haven't done this type of work, basically what we've got is 100% control would be a dead weed or a dead pest, and 0% control would be no application or no injury observable from that application. So if we look at that set of brown bars again, you can see we've got our XR nozzle had the highest level of control. We had a slight drop off when we get to that drift guard, and then when we get to that extremely coarse application or that turbo flood, you can see a significant drop off in terms of the efficacy that we get from that. That's that trade-off between droplet size and coverage. So the larger the droplet size gets, the less the coverage gets. Now, just like that, what we see is that as we reduce the spray volume, we're also going to reduce the coverage. So if we look at the 10 GPA versus the 7.5 versus the 5 GPA, you can see slight decreases as we reduce the volume within the XR nozzles and the DG nozzles, and then the turbo flood nozzles as well. And that's because we're giving up coverage by reducing volume. So when we talk about contact-based herbicides like paraquat, we've really got to make sure that we're targeting coverage. There's really 3 ways that we can increase coverage. First is increase volume. The second is going to be decrease the droplet size, and the third one is going to be adding some sort of a spreader or a surfactant to that application. Obviously, if we decrease droplet size, we're talking about an increase in drift potential. So if we want to balance the efficacy and the drift potential, decreasing the droplet size is not going to be the optimal way to do that. We really need to push towards using higher volumes. Now, this next slide is really some work that was conducted by Paul Fang and his group at Monsanto. This one is now looking at a systemic-based herbicide. They used an XR nozzle to produce a fine spray droplet, a Turbo T to produce a medium spray droplet, and then a AI nozzle to produce a coarse spray droplet. And what they did then is looked at the absorption and translocation of glyphosate on Roundup Ready corn, and what they found is that the smaller the droplet size, the less absorption or uptake they got, as well as the less translocation they got or movement of that glyphosate throughout the plant. So here's one of those opportunities with glyphosate that we can actually push towards those larger droplet sizes without giving up any efficacy, but yet we're also going to be mitigating or reducing the drift potential at the same time. Now, the next couple slides are some work that one of my former students, Dr. Cody Creech, put together from some of his research. And what you see here is the impact of nozzle type on droplet retention. So I don't know if it is probably cut off on your slide. I can't see it at the bottom of mine, but what we have are 3 different nozzles going across the x-axis. The first one is going to have the smallest droplet size, which is observed by the black square in the green bar. Going to the right, you can see the droplet size getting larger from 250 to approximately 500 microns to a little bit larger than 750 microns for the 3 bars. What those 3 bars are an XR, AIXR, and a TTI nozzle going left to right. And so as we change that nozzle size, we increase the droplet size. The green bars that you're looking at that you see stair-stepping down are the relative fluorescent units, or how much product was retained on the plant at the time of application relative to those 3 nozzles. So as we increase droplet size, you see that inverse relationship, or that decreased droplet retention on the plant. Now, when he did that, he also did some work looking at different adjuvants. And so you can see going across that x-axis now, we've got methylated seed oil, or MSO. We have a non-ionic surfactant, or NIS, silicone surfactant, crop oil concentrate, a drift retardant, and then in this case, just straight water, or we looked at a couple different herbicides without any adjuvant system. So that data is pulled across those herbicide systems. And if you look at the black dots again, or those black squares, what you see is the droplet size is kind of bouncing around between about 485 to 520 microns in size. But really no correlation in terms of retention. So this is telling me that we've got an opportunity to use some adjuvants to increase retention without affecting droplet size. So this is an opportunity to increase the droplet retention or increase efficacy without compromising that particular application from a drift management standpoint. So we're getting a little bit better coverage or retention on that leaf surface without giving up or increasing the drift potential. So with the remaining 40 minutes or so that we have, I really want to start digging into several different field studies that we've conducted. So the next few studies are going to be laid out very similarly. What you see in the top right-hand picture is some different weed species and crop plants that we planted in the field. We plant those in a row and then we spray across. You can see that picture is for an untreated check, but some of the other plots we would spray different applications. So these studies were conducted at 4 locations in Nebraska. At each location we had 4 replications, and you can see the 5 different species we listed there. Due to time, we're not going to have the ability to look at every single one of those species for every single herbicide that we looked at. But what we did is for each herbicide we looked at, we used 5 different nozzles, an XR 11002 giving us a fine spray quality. We used the XR 11003 operated at 43.5 psi, which is that reference curve from the ASAB S572 standard, which has been referenced in the previous 2 webinars as the boundary between the fine medium. And then we used Turbo T 11002 to give us a medium spray quality, and AIXR 11002 to give us a coarse spray quality, and then an AI 11002 to give us an extremely coarse spray quality. This again was part of Dr. Creech's work as a PhD student, and it really gave us an initial look at what was going on and why certain labels had certain application information in them. So what you see here is is the glyphosate application on amaranth. And I want to point out before we dig into this data too much that for this study, we did use a half rate or half of the maximum labeled rate for each of the products. In this case, we were even a little bit less than what most people would consider a half rate with the glyphosate, and we used 11 ounces per acre. And the reason we do that is if we get 100% control, it becomes very difficult to tell what's going on from a droplet size perspective. So we try to reduce that rate to get partial control. And then the amaranth that we used here, I know many of you instantaneously go to Palmer or water hemp. In this case, we use a grain amaranth, and the reason that we do that is because it's very, very difficult to get a consistent weed population when you seed it in with some of these other crops. So we get just a little bit more uniformity, makes the ratings a little bit easier to manage. The downside to doing that, as many of you know, we've got a lot of different herbicide resistances in those two weed species. The grain amaranth is not been selected for glyphosate resistance or other resistances, so it's still very, very susceptible. And you can see that here where 11 ounces has given us between 95 and 98 or 99% control across the treatments. Now, what we have here, we've plotted the droplet size on the x-axis. This is the DV10 value. So if you're thinking that a 250 micron droplet is extremely small for an extremely coarse, you'd be correct. The reason we plotted it against the DV10 values in this case is we wanted to show the drift potential of that application. So for those dots that you see on the figure here, the farther that dot is to the left, the greater the drift potential. The farther up that figure the dot is, the better the weed control. And so we start to look for the trends to determine what the optimum application scenario would be for each weed species and each crop or each application that we use. So in this case, you can see we've got a very linear type response, not much difference between control for each of those applications. So we really are looking at trying to mitigate droplet size because the efficacy is about the same regardless of which droplet size we're talking about. So in this case, with glyphosate, the recommendation would be to use an extremely coarse droplet, maybe even an ultra coarse, even though we didn't push that far in this particular study. Mitigate drift as much as possible since we're not giving up any control. Now on the next one, this is now dicamba, and again, if you look across here, it might look like the extremely coarse is just a little bit more efficacious even than the fine, the medium, or the coarse. But there's no statistical difference in terms of the control across all 5 of those treatments. But what we do see, again, is a very, very linear response for dicamba, whether we're talking about clarity applications pre-plant or in corn, or the new formulations in soybeans or cotton. We're really going to push towards using as large a droplet sizes as possible because we're not giving up that efficacy and we want to mitigate drift as much as possible. Okay, for the next one, we use fomasafen. Again, this is on that amaranth population. Now you can start to see that we're getting a little bit more difference in the different droplet sizes. The extremely coarse doesn't really follow the trend of the first 4, but you can kind of see where that fine medium looks a little bit better than the fine or the coarse, and we'll come back to why that extremely coarse might be a little bit different a little bit later in the talk, but we're starting to see 10 to 15% difference in some of those treatments. I left the letters off of there for statistical separation just to keep the slide a little bit cleaner, but we did have some statistical difference between the treatments. The reason we see the fine drop off and then the efficacy go up to that fine medium or medium is really due to loss from drift. And when we see the the drop off from medium to coarse, that's due to coverage issues. So if we start to look at some of these products like the post-emergence PPO inhibitors, we see specific label recommendations on volume in particular, as well as droplet size. So for example, some of the labels will say use a fine or use a medium or use a coarse, or maybe use a medium to coarse spray quality. And that's really because they've done, different companies out there have done a lot of work trying to understand what that optimum range might be, but yet they want to keep you from having any more drift than necessary with those products. When we look at that, and here's the first one that we've looked at a different plant with the same herbicide. This is now foamosaphen on flax. You can see when we go from that medium to coarse, we get almost a 30% drop off. For those of you online that know or have worked with flax, you know that it's a very upright plant. It's got very small leaflets. It's very difficult to wet, and it's difficult to get droplets to stick to that leaf surface. So for contact herbicides, that can be quite a problem. And we see that as the droplet size got larger and larger, we lost that coverage, and you can see the control now dropped nearly 30%, and that's extremely significant. And even our practitioners in the field, if you're walking different fields that would have a plant with that type, weed species with that type of morphology, you would see that difference in control when you went from a medium to a coarse spray. Okay, the next one we're looking at here is now clethodim. The clethodim, I've used the volunteer corn, or the corn population that we planted, the artificial volunteer corn. And the reason we aren't looking at the amaranth or the flax now is because this is an ACCase inhibitor, so it's a product that's only going to have grass weed control activity. So here you can see that medium again pops, but it's kind of all over the board. And this again comes down to the fact that there's very, very specific interactions between the weed species we're targeting and the herbicide we're using. With corn, as many of you know, we've got a very a narrow leaf, a long leaf, and that leaf is not perpendicular to the application, so that leaf is going to bow out and droop down, making it easier for larger droplets to hit that leaf surface and run off. So even though we've got a systemic, we're seeing that there's a drop off in efficacy as we get these larger droplet sizes. With that variability that we saw in a couple of those, it really had us scratching our head as to exactly why we're seeing so much variability when we go from one spray quality to another. So we took a step back and reevaluated what we were looking at, and revised the study a little bit to look at things from a little bit different perspective. And this is where the light bulb really started to go off for us. Okay, so for this study, what we did is we added carrier volume in as a factor. So for this one, we looked at 4 different herbicides, 4 locations across Nebraska, and we looked at multiple different carrier volumes. Again, plot size and the ratings and stuff like that were identical to what we'd done the year before, but this time we really had interest in looking at contacts versus systemics. So the 4 herbicides we picked, the first was Roundup or glyphosate. I've put 3 GPA. That's just a reminder that the minimum volume for a Roundup Power Max application is 3 gallons per acre. The other systemic herbicide that we chose is down at the bottom of that list. That's 2,4-D, and that one had a minimum of a 10 GPA application on the label. The 2 contacts you'll see have higher minimum volumes. The first one being glufosinate or Liberty at 15 gallon per acre, and then Lactofen or Cobra at 20 gallon per acre. Those contact-based products, we need that volume to get the coverage. And then in terms of application, we looked at 5 different carrier volumes, and the way we put those carrier volumes out, the 5 GPA was put out with an XR 11001 nozzle at 4 mile per hour. The 7.5 gallon per acre application was again an XR11001 at 4 mile per hour, and the 10 gallon per acre was identical to that. When we went to the 15 gallon per acre application, what we saw was, or what we did is we went to an XR110015, and then for the 20 gallon per acre, an XR1102 at 4.8 mile per hour. And the reason that we switched nozzles for those last two is that we're using a backpack sprayer to make those applications. So we had to increase the pressure to keep that nozzle and ground speed the same. At a point when you're using a CO2 tank to increase pressure, you get to that point where you're not comfortable going any higher, and we also would exceed the nozzle manufacturer's recommended pressures for those applications. So we put a larger orifice size on so that we get that flow rate. If you're walking an application on, we could have walked slower, but we really didn't want to do that because we felt like it would be more difficult to get a nice uniform application. So we go to that little bit larger orifice size. Now I go through all of that explanation on those 5 treatments because it's really important in terms of what we found. Because as we increase pressure, as we talked about in the previous or in the first webinar on ground applications, that droplet size is going to get smaller. So when we went from 5 to 7.5 gallon per acre, we got a smaller droplet size. When we go from 7.5 to 10 gallon per acre, we get a smaller droplet size. However, when we increase that orifice size, we were able to drop pressure back down and increase the flow rate, giving us a larger droplet size, and then the same thing from 15 to 20, meaning that the 10 gallon per acre has the smallest droplet size of all of the applications. Now, when we looked at the results for this, here you can see that efficacy again on a scale of 0 to 100. We've got 5 GPAs listed out side by side with the shading going from white to black. With the 2,4-D, what we see is no statistical difference between the 5 different GPAs. And the glyphosate on the right-hand side, the exact same thing. Those are, again, our 2 systemics. When we look at the 2 contact-based products, you can see that we get an increase in efficacy as we increase the volume, going from 5 to 7.5 to 10 to 15 to 20. Again, as we increase that volume, you can see the efficacy continue to increase. On velvet leaf, we've got a plant that's got a very hairy leaf surface. Having that additional volume allows us to get that droplet past those leaf hairs into the cuticle. When we looked at amaranth, though, we saw a very similar story, slightly different in terms of we didn't get as much statistical separation, and you can see that the efficacy really started to plateau out when we got to about 10 gallon per acre. But again, the 2 systemics, no statistical difference, where the 2 contacts we see increased efficacy as we get those higher volumes. Okay, now when in this next slide, I just really wanted to show you what we were seeing in the field. So this is the lactofen on the left at 5 gallon per acre, and the lactofen treatment on the right at 10 gallon per acre. And we've now put a little red circle around the amaranth, and you can see on the left a very, very different situation than we have on the right. If we were to show you the picture of the lactofen at 20 gallon per acre, there wouldn't be any amaranth. We got complete control at that point. So what you see in terms of that amaranth control, for example, is of a difference that would show up in the field. This would be a respray on the left, where on the right we probably wouldn't notice the weed escapes there. Okay, this is the last slide related to this study, but this is really where the rubber meets the road. What you see is the amaranth control coupled with the droplet size for each of those 4 herbicides across the 5 carrier volumes. And what we've done, we've plotted out the droplet size in the black boxes, and we've plotted out the control in the black triangles. For the 2 systemic-based products, what we see, again, that droplet size is the smallest. with 10 GPA, and the droplet size gets larger as we go either up or down in GPA. With the exception of the glyphosate at the 5 gallon per acre down in the right-hand box, and I'll come back to that in a moment. When we look at the two contact-based products, what we see is that again, the droplet size is the smallest at the 10 GPA, but the two lines are no longer paralleling each other, so we don't see that control following the droplet size. What we see is the droplets, or the control, or those black triangles, as we move right in those two boxes, getting higher and higher, or as we move left, those lines are dropping lower and lower, indicating as we increase droplet size, we're increasing control, or increasing volume, we're increasing control, or where we're moving to the left, we're decreasing volume, we're losing control with those two contacts. So the real take home on this is that if I'm dealing with a systemic, most of our systemics we're going to manage or maximize efficacy based on droplet size, with actually larger droplet sizes in many cases being more efficacious. With our contacts, we're going to maximize efficacy by increasing the carrier volume. So that really starts to take us down, or to take us down a little bit different path. So the next study I want to talk about is a study that we conducted in North Platte. What we did is we used a calf stand pinpoint system. This is some work that another one of my former students, Dr. Tommy Butts, conducted. And what we did is we used that pinpoint system, or the pulse width modulation system, to deliver specific droplet sizes. So what we would do is we go into the wind tunnels in the lab in North Platte, determine what treatments would give us specific droplet sizes, so which orifice size and pressure gave us a specific droplet size. Then we would take that to the field to deliver a constant volume across a uniform or single tank mix. So just to give you a little bit of feel, we looked at, for what we were looking at, we looked at 150 to 900 micron droplets at both 5 and 20 gallon per acre, using both glufosinate and dicamba. On this slide, you can see the combinations of nozzle, orifice size, and pressure, as well as the ratio of that pre-orifice to exit orifice in those Wilger nozzles that we use to deliver each of those different droplet sizes. So going again in 150 micron intervals from 150 to 900 microns. And this next slide shows you the combinations that we use to get the same treatments for a dicamba tank mix. Now, I do want to point out that for both the glufosinate and the dicamba, we did not use any spray adjuvants, knowing that those spray adjuvants would affect the droplet size for those applications. And when we dug into this, what we found is that we see different droplet sizes for both the glyphosate and or different optimum droplet sizes for both the glufosinate and the dicamba based on the GPA. In this particular study, what we're seeing is that the optimum droplet size for the dicamba application at 5 gallon per acre was 150 micron treatment. At 20 gallon per acre, the optimum droplet size was 600 microns. Whereas for the glufosinate at 5 gallon per acre, the 300 micron treatment seemed to optimize efficacy. And at the 20 gallon per acre, the 450 micron droplet seemed to optimize efficacy. And we'll talk about why we think that happened in a moment. Okay, oops, just get past a slide. Sorry about that. when we ran when Dr. Butts ran the models for that data, he used a GAM model, which you can see here on the slide. And basically, what we're trying to do is account for the deviance of that regression model, and you can see change in droplet size in this particular study. We could account for about 57% of the variability in efficacy across those different treatments for both the 5 and 10 gallon per acre. And you can see we've got some funny things happening, and part of that is due to one of the treatments that we had at one of the locations. Now, when we kind of show you some pictures of this, you'll see very clearly for the glufosinate application, that 300 micron droplet at 5 gallon per acre, I said was the optimum treatment that we applied. You can see we've got pretty good control. So even at 5 gallon per acre, we can get pretty good control with Liberty or glufosinate. But keep in mind, that's a really small droplet size. It's going to have a really high drift potential. The one way that we can get into a little bit larger droplet size is to increase the volume. And if you think back to a couple of slides ago, we said the 450 micron droplet was optimum at the 20 gallon per acre. By increasing that volume, we were able to increase that droplet size a little bit, yet maintain or maximize the efficacy for that particular tank solution. As we go from 300 microns down to 150 microns, you can see a significant drop off in control. This is a lot of times due to drift or to applying droplets that are so small that they never really reach the target in a liquid form. As we get larger and larger droplet sizes, you can see going from 300 to 450 and then 600, 750, and 900. You can see that efficacy drop off. And on the large side, this is because we're losing the coverage. Now, here's the GAM model then for the dicamba. Again, even less of the deviance explained, with only 28% of that deviance now being explained by the change in droplet size for dicamba. And part of this is due to the versatility of dicamba. What you see when you look at the pictures here, going from about 300 to 750 microns, we see very, very little difference in terms of the efficacy. And you can kind of see that in the pictures. And we even at 150 microns have fairly significant control compared to the control in that left-hand box. What we did see that was consistent across both the Liberty and the dicamba at 5 gallon per acre, though, as we got to that 900 micron droplet, there's not much difference in that treatment versus the control. We've just, even with a systemic based product, got too large of a droplet size at too low of a volume to get coverage and control. Now, when we take those GAM models, we can actually predict what the optimum droplet size is across the entire range tested. So we're basically drawing an interpolation between the data points now. And looking at that 5 gallon per acre for the dicamba, you can see 150 micron droplet, the smallest one we applied, is optimum. Whereas we go up to the 20 gallon per acre, we're now our absolute optimum droplet size was predicted to be 626 microns, or an extremely coarse. So if I'm wanting to reduce drift, in the case of dicamba, I got to increase the volume. If I'm wanting to reduce drift with the glufosinate, again, you can see the same thing, where 5 gallon per acre, the optimum droplet size was 270 microns, and at 20 gallon per acre, the optimum droplet size is 488 microns. So I increase that volume, I can increase the droplet size that's maximizing efficacy, I can reduce drift. Okay, so this next set of stuff studies that I want to talk about are really looking at tank mixtures, and this is what some data that was put together by one of my current students, Jessalyn Morris. And what we see here are 4 different species that we looked at: horseweed, kochia, lamb's quarters, and grain sorghum. And Jess kindly put a note on here for me to remind you guys that the horseweed population, that coniacids population that we were working with, was glyphosate resistant. And the different treatments that we were working with here, or different pesticides and adjuvants we were working with here, were glyphosate. And with that glyphosate, and this is not meant to be an endorsement of any of these products, but the glyphosate product we used was Roundup Power Max. And I tell you that because different products are formulated differently, so that brand name or that product name is very important in terms of understanding the droplet size and some of those components. So glyphosate, we use Roundup Power Max. For lactofen, we use Cobra. For the fomosafen, we used Flexstar. And then with AMS, we used a dry AMS product at 17 pounds per 100 gallon. That was added to all treatments in the study, and the crop oil concentrate was added. It was an 80% crop oil concentrate, and was added to all treatments except for the glyphosate alone. In this study, we looked at a range of different nozzles: XR, AIXR, TTI from TJet. We used a Guardian Air and a ULD from Hypro, and a TDXL nozzle from Greenleaf for AgroTop. And you can see the different features of these nozzles. All of them are air induction nozzles, with the exception of that XR, or extended range nozzle. And those nozzles give us a wide range of different droplet sizes. Now, as we start, and I'm gonna push through this this study a little bit quickly, so kind of stick with me. Here are the application parameters. We're using 187 liters per hectare, 9.6 kilometers per hour, and 276 kPa on a 3 nozzle track sprayer that we have in the lab. Nozzles were spaced 50 centimeters apart, and the application was 50 centimeters above the plant. What we, when Jess summarized the data from this, you can see the ANOVA here. The only thing that we saw, the only interaction that we saw significant, was that herbicide solution by weed species. When we got the 3-way combination of solution by nozzle by species, it wasn't significant. So what we did is we pulled the data across the data that's presented in this presentation across those different nozzle types. Then the first thing I want to show is the droplet spectrum. So if we start thinking about drift, understanding the droplet spectrum is going to be very important. For the glyphosate alone, that's where we saw the smallest droplet size. Anytime we had lactofen or fomosafen in the tank, we saw an increase in droplet size for the XR nozzle. Same thing is true for the Guardian Air, with the exception of the glyphosate plus lactofen plus AMS plus COC. And then again, that same treatment for the AIXR. When we look at the TDXL, again, the same thing we see with the fomosafen and lactofen, an increase in droplet size, decrease the droplet size when we add that glyphosate to the tank. With the ULD and TTI, we see a decrease with fomosafen, and we see an increase with the glyphosate plus fomosafen in terms of droplet size. So a little bit different reaction in terms of droplet size. Going back to what we talked about in the first webinar, where we have these interactions between nozzle type and tank solution. This is just a line graph showing the same thing. This is looking at the percent fines now. You can see that XR nozzle, that yellow line, is the highest, and we're seeing the most driftable fines with that nozzle, regardless of tank solution. And for most of these, you see a little bit of a bump here where we have glyphosate alone, and that's due to those surfactants through those different nozzles. Again, you can see things like that purple line or that AIXR, where we're getting a little bit slightly different interaction there. So keep in mind, as we think about applications, there are interactions between nozzle types and tank solutions. Okay, so now we want to take this data, and we've talked about how different individual contact and systemic products work, optimizing efficacy. This time we're going to use the Colby equation to try to explain what we're seeing from a tank mix response. So the Colby equation accounts, or is the response of different herbicides applied singly, then used to calculate expected responses, and then compared to the products when they're applied in combination. And that comes from a paper back in 1967. So basically, the way we calculate that, you can see the expected here is product 1 times product 2 divided by 100. So basically what we're looking at, we take that first product and we subtract, we take 100 minus that, giving us that observed response for the first herbicide. For the second product, we have 100 minus that second product, where Y is the observed response for that second herbicide. The expected then is 100 minus E. And so the expected response is that response of the herbicides A plus B. So just an example of what that looks like. Here we have observed response for herbicide A at 30%, B at 50%, and A plus B at 80%. We go through the equation, so we go 70 or 100 minus 30, giving us X1, 50, or 100 minus 50, giving us 50 for X or Y1, and then divide that by 100, gives us 35. E then is 100 minus 35, or 65. So we plug that 65 into the expected, and what we see here is a synergistic relationship, because the observed at 80 is significantly higher than the expected at 65. If we have something where we have product A is 30, product B is 50 now, they're identical to the previous one, but now the combination of the two is 65. So 65 and 65 are the same thing. We've kind of worked through that equation the same way. We now have an additive interaction. And lastly, we have now this, again, product A 30%, product B 50%, but we combine the two, we get 42% control, expected 65. We work through our equations, same way we did for the first two. We now have an antagonistic interaction where that expected control should have been higher than what we were actually observing in the field or in the lab. So we took those different treatments that we had. You can see the observed values here for glyphosate alone, on horseweed and kochia, the lactofen alone, the foamosaphen alone, and then you see the tank mixture of glyphosate plus lactofen and glyphosate plus foamosaphen. We've got our observed responses. You can see a decrease in the overall efficacy of those PPO inhibitors for horseweed, a decrease in the efficacy of the foamosaphen for the kochia, And so we kind of get a little bit of idea what we're expecting here. We plug in the numbers of the products by themselves through the Colby equation, calculate our expected values, and what we see is for the horseweed with the lactofen plus glyphosate, we're expecting 65% control. We observe 42% control. We see an antagonistic interaction there, and the same thing with the fomasafen plus glyphosate. When we looked at the kochia, you can see the expected is very similar to the observed for the glyphosate plus lactofen. We've got an additive interaction there. However, when we look at the fomasafen plus glyphosate, you can see we expected 88%, got 77, giving us an antagonistic interaction there. And what we have here is just some pictures at 14 days after application, and you can see the different nozzle types now on those kochia plants. So you can see the untreated with the glyphosate glyphosate plus fomasafen tank mixture with the XR and TTI nozzle, and the same thing with the fomasafen applied alone. So you can see the fomasafen alone much better control than when we added the tank mix. So that glyphosate is antagonizing that activity of the fomasafen. When we look at common lamb's quarters and grain sorghum, you can see our observed control, 92 and 98% for glyphosate alone. When we look at lactofen, and fomasafen, we have less control. But when we look at the tank mix of the two, we've got better control than either of the PPO inhibitors alone. Same thing for the grain sorghum. However, when we look at the expected values, because of the activity that we're getting out of the glyphosate, again, we've got antagonistic interactions on lamb's quarters and antagonistic interactions on the grain sorghum, even though we're getting 96 to 97%. Now, I know I've got some people out there that are technically savvy in this area, and when we get that high of control, we do want to be a little bit careful. When we get that high of control of any one product alone, we're in the 90% range here with glyphosate. We want to be a little bit careful how we interpret that, and we probably don't, or we may not have a true antagonism here because of that. Okay, again, what we find, here's some different citations in the literature looking at glyphosate and PPO inhibitors and kind of confirming what we observed in the greenhouse, that we see a reduction of glyphosate absorption and translocation due to the use of those products. All right, so now that we've kind of worked through that, I apologize, it's a lot for 1 hour. We've now exhausted the hour. I've got a few take-home messages here. They're very similar, or they're the same ones that we had on the first webinar. I'm going to tell you that these are really important takeaways related to drift and drift management. And it's been an exciting series to go through this. Some of the take-home messages that we just don't want to forget. Particle drift can be influenced by formulation. We saw that over the series, looking at both ground and aerial applications. We've seen that nozzle selection has the greatest influence on particle size. Again, true across ground and aerial applications. Although remember, as Brad talked about in the last series, that application airspeed really becomes another layer of complexity for those aerial applications, as does that deflection angle of that nozzle in the airstream. Adjuvants can be used to reduce drift potential, but you want to be cautious of which nozzles and application scenarios you're pairing those up with. Please remember there's no substitution for common sense. If the wind's blowing, droplets are going to move. We see off-target movement with every application, so we want to talk about how can we minimize that off-target movement in every case. We need to be paying attention to what's around us, and drift, like we said, is going to happen. Mitigating drift in every way possible is absolutely essential, as long as we're not giving up efficacy. With that, we're going to open this up to questions. So I'm going to turn this back over to Quay for a couple notes on logistics.
And now we will go through your questions. In balancing drift versus efficacy, when does droplet size get too big? For example, droplets too large to be retained on the target.
Yeah, thank you, Quay, and thank you for the question. This is going to be one of those where it's really important to recognize that that question is incredibly difficult to answer. It's going to be product or tank mix specific, and it's also going to be target specific. So kind of like what we showed today, different species are going to respond differently to different droplet sizes, as are different species response to different herbicides. In some cases, like dicamba or glyphosate, as we showed, we can move to large, extremely coarse or even ultra coarse spray qualities without giving up efficacy. In other cases, with some of these contexts, we got to be real careful that we don't get those droplet sizes too large, because we will see that control drop off. So it's a difficult question to answer simply because there's so many interactions going on there.
Next question. What do you suggest as an approach we can take to optimize the balance between drift and efficacy, particularly where there may be a lack of information like that presented?
So another good question. Thank you. Whoever submitted that one. As we start to dig into this more, we're seeing that there's so many interactions that that's difficult to say as well. What I would say is, as we think about the different types of products we're using, we do know that we can increase volume in all cases, and a lot and everything we've seen to this point, we don't dilute out that effect. It's possible that we can get incredibly high volumes and we wash out the activity of that pesticide, but in that normal range for a broadcast row crop ground application going from 5 to 20 gallon per acre, we didn't see any loss in efficacy there. So pushing those higher volumes is one of the best ways to start to do that.
Okay, next question. For plant protection products applied directly to cultivated crops, do these same principles apply? For example, increasing the volume to increasing droplet size in order to maintain biological efficacy?
So I'm not sure I completely follow the question, but I'm going to try to answer based on my understanding of the question. So when we talk about different crops that we're applying to, it's really about what weeds or what pests we're trying to control in those crops. So again, those weeds, whether I'm spraying them in a corn or soybean field, or I'm spraying them in pasture, or some sort of specialty crop, we're going to see that the efficacy is going to be the same. We're going to have that same efficacy relationship across different crops. When we see the principles are going to hold true in terms of volume, what we tend to see that's different is that if I go to, for example, a turf grass application, what I consider a low volume is going to be very different from a ground application. So there is going to be get us into a whole lot of different scenarios that we probably don't have time to cover every one, but in general we do see the same thing going from one place to another.
Next question. If you get optimum control from either 300 microns and 5 gallons per acre, or 450 microns and 20 gallons per acre, would you as a farmer really choose the larger particle size and larger volume? You're putting down 4 times the product.
I'm not putting down 4 times the product. I'm putting down 4 times the water. We would keep that product rate the same. Yes, it's an inconvenience to put down more volume, but if I can do it in a safer, more efficacious way, or safer or more efficacious way, I'm going to look to do that. And I say that it's a little difficult to say because I grew up on a farm. I know how precious time is, and the more volume we've got, the less acres we're going to cover with a single tank load. So the temptation is going to be really strong to go to that 300 micron 5 gallon per acre application. But again, from a stewardship responsibility, from a sustainability standpoint, I'm going to look to move that application to that 450 micron 20 gallon per acre application.
Next question. Is there a clearinghouse or a resource where we can find the type of information presented here to help in making application management decisions?
Another good question. The only place I know to go is really some of the stuff that we presented today, or the pesticide label. I really didn't emphasize that second one well enough today. But if you dig into the pesticide labels, there's a lot of really good information. We talked about that in the first webinar. If you look in that pesticide label, there's information on how to apply products. So it tells me to use specific spray qualities or minimum GPAs. Whenever I have a question about how to optimize that pesticide application, the pesticide label is going to be the best place to start.
Thank you for joining us. Have a nice day.